So you should have attempted that Desmos activity before watching this video. And what happened in that Desmos activity is we got our first introduction to this idea of having more than one sample, those two sample inferential methods. So we had those two examples, research question 1, where we were dealing with dolphins, and research question 2, where we were dealing with that bike commute. So in both of these situations, we actually had an explanatory variable and a response variable. So in the dolphins, it was like, did you swim with dolphins? Oops, that's not how you spell dolphins. Dolphins. And does that influence your depression, right? And of course, both of these happen to be recorded in a yes, no. Like swimming with dolphins, either you did or you didn't. Depression was, did your symptoms improve, or whatever they had, a yes or no. So they're both categorical. And then for bike commute, you were looking at the type of bike and then the time for his commute. And we had a categorical. In this case, we had steel versus carbon fiber. Oops, can't spell that either. And actually carbon fiber was first, I think, in the two samples. And then the commute time, which was a quantitative variable. So we got our first sort of example here of this two samples. And the reason we have two samples, because in both of these, our explanatory variable broke everybody into two groups, right? So in the first one, it took all of our people who were part of our experiment, all of our subjects, and it split them into these two groups, whether they swam with dolphins or without. And in the second one, we had that, I don't remember what he was, a researcher or whatever, who was flipping a coin to decide which bike to ride to work. So, and there were only two options. So we have these two different options. So this is where you started saying, oh, well, if we're looking at a categorical variable versus another categorical variable, we could go ahead and display that with a stacked bar chart, right? So that's what we got for the dolphin one. And that stacked bar chart was pretty dang convincing that dolphins were very helpful, because I think 10 out of the 15 who swam with dolphins got better, whereas only 3 of the 15 who didn't swim with dolphins got better. So we're immediately going like, dolphins. And then the bike commute, since we were looking at a categorical variable versus a quantitative variable, our display was a set of box plots, one for the steel frame and one for the carbon fiber. And what actually happened when we looked at these is they were pretty dang similar. We couldn't see a huge difference in the two box plots. I don't remember exactly what they looked like, but there wasn't a huge overwhelming piece to this. And then also, we saw our first use of this subscript. So in the dolphin example, if we're looking at a categorical variable, we're just going to count up the number of yeses. That's the easiest way to summarize this data. So in this case, we had these two groups. We had the dolphins group. Oops, that's terrible. And the no dolphins group. Is that really how I spell dolphins? It looks so weird. In the dolphins group, we had both of these groups. I think there were 15 people, so we called that N1. We called this N2. And then we had the number of people whose symptoms improved in both of those. So, oops, that's a 2. So we had these sort of like subscripts for the first time of like, okay, we need multiple ways. We need to have the exact same data for two different groups, so we'll just use this subscript. So 1 means dolphin, 2 means no dolphin. Same thing with the bike commute, but here, since our variable was quantitative, our summary stats took the form of X bar. So we had X bar for the carbon fiber. I don't remember what the number was, so just bear with me as I just guess. And then we had an X bar, oops, for the steel frame as well. And they were really, really similar, so there wasn't a whole lot of difference. Again, I'm just making them up, but showing you this idea. So what is it that you need to know? Well, this comparing of two variables is exactly what you're going to be doing in your project. So if you happen to have a categorical variable that splits your data into two groups, you might end up doing something like what we just saw. And with what we just saw, we have a potential ho and ha, right? A null and alternative hypothesis for both of these situations. So for the first situation, we could summarize this X and N for both groups with a p hat, right? And I did in my little summary stats piece. And if we were going to compare these two groups, we would compare the real proportion for each group. So this would be about p for both groups. the proportion of people who improve who swim with dolphins is the same as the proportion of people who improve who didn't swim with dolphins. Dolphins don't matter. And then we'd have, of course, probably some other metric here. In this case, they thought people were going to see more improvement if they were with the dolphins. So there was a greater than. In the bike example, now we're talking about a quantitative variable. So of course we're in means land. And our null hypothesis is going to be the two means are equal. The average commute time is the same whether he uses his carbon fiber bike or his steel bike. And then our here, well, this one was a little bit funky. Any of us who know anything about bikes are probably thinking the carbon fiber is faster. It is a lighter bike. But they just did a 2-sample test. There was no words inside of that to indicate that he wanted to show it was faster or that its commute time was less. So we're just going to use a not equal to. But this is basically what I care about from the 2-sample. I want you guys to be able to set up your hypotheses. That is a clutch move, right? To be able to set up what it is that we could test using 2 samples. That's the first thing I want you to do. The second thing I want you to be able to do is to check conditions, right? Those conditions are always vitally important. If we don't have them met, then we really shouldn't proceed with what we're doing. So the conditions for these 2 tests, of course, are slightly different, but very similar. So I'm just going to go ahead and do them together and then break them up when I need to. So the first condition we need is we need the same thing we had before, an SRS. I'm just going to call this the randomization condition. If I could spell, I would spell it correctly. Randomization condition. And there's actually 2 ways we can meet this randomization condition for a 2-sample test. We either take independent samples from each group, so in this case, we would go ahead and we'd take a sample of people who swam with dolphins and take a sample of people who didn't swim without dolphins. That would be legit. One thing we cannot do, the one thing that makes this test a little bit sketchy, because the way we will use it in a lot of situations, we don't meet this requirement. And so we sort of just, I don't know, hand wave to say we're going to do it anyways, is if you take one sample and then you split people up. So if you take one sample and then you like split into male and female, this technically violates this independence. Technically, we should not be doing a 2-sample t-test if we're just asking people a question and then separating them after the fact. We would need to actually take a sample from that group instead. The other way we can reach this, which is how we reached it in our 2 examples in that card sort, is that we could have random assignment into treatment groups. So let's put a big or. So in both these cases, if you didn't answer this in the card sort, you got it wrong. But these are both experiments. In the dolphin one, people randomly assigned whether they swam with the dolphins or not. And in the bike riding one, he flipped a coin to decide which bike he rode each day. So random assignment into the groups is how we meet this for our examples in that particular, the thing we were doing, the card sort. The second thing we need, same as before, we need our N to be less than 10% of the population. So we still need that piece, right? So all the people who are depressed who might swim with dolphins, all the people who are depressed who might not swim with dolphins should be more than whatever, 150. Great. Same thing with our bike ride. Perfect. Whatever. Sure. We got this. We don't have to worry about that. The third one, and this one matters a lot, is we need to make sure that we have normality, right? That we have the ability to use a Z or a T, that we have this cute bell curve going on behind the scenes. And so this is where we split based on proportions or means, just like we did before. So if we're dealing with proportions land, right, if we're in the P1 is equal to P2 and we had categorical versus categorical, well, then we know typically we're looking for NP and NQ to be greater than or equal to 10. Now the issue here is we have 2 different N's. Oh crap, I should have even mentioned that in the previous one, right? N1 and N2 are both less than 10% of their respective populations. So same business here, we're gonna use the ones. Technically, Some books will use P1 and Q1, which makes sense, the proportion from each group. But since we're in that null, right, since we're saying that we think that P1 is equal to P2, what is technically correct is to use here a PC. This is a P combined. P combined is just going to be all of the successes, right? So in our example, we had 10 people who got better who swam with dolphins. We had 3 people who got better who didn't, out of all 30 total people. So we had 13 out of 30 people improve regardless of their treatment. That's our PC. Now, I'm not going to test you on this nuance between PC, P1, but just know we do want to make sure that we have every single group, the expected number of successes and the expected number of failures is greater than or equal to 10. And I did do a bad thing here. I left off my hats because technically in this case we don't know real P, real Q. So we're using P hat, Q hat, and same thing with our PC. It's a P hat. Oops, that should have been Q. So all of this stuff has to be greater than or equal to 10. If that's true, then we have normality. So in our particular example, it's not true. If we multiply this by our original n of 15 times that 13 over 30, we're going to get out 6.5. So we technically don't meet normality. For the dolphin example, we should have probably used a different method. Now for means, we know what we're looking for in means land. I'll just make a big line so we know this is means land. We have 2 options, right? Either X followed a normal distribution in the first place, and in this case we do have 2 different populations, so they both need to be normal, or our samples were both greater than or equal to 30. Oops, that's a 2, and that 30 is ugly looking. And in this case, we know, I think with the bike riding example, I don't think he had 30. I can't remember exactly what the number of times he rode his bike was. But if you don't have 30, you'd want to say that these things looked approximately normal. From his box plots, we didn't have any huge violations. So for the example with the bikes, we would be okay to say, yeah, it doesn't look like there was any crazy days where he took a really, really long time or a really, really short time. So conditions are met. But that's the second piece that I want you to know. Hypotheses, conditions. They still sort of fit. We just really modified them slightly for the 2 groups. But each group has to match all the conditions we had before. The randomization probably being the most important one here, because that's going to be the one that we're going to violate in our projects, because we're just going to go out and take one horrifically terrible sample and then split people. So after that, the rest of this, or the rest of it, but the test stat and the p-value, these are things that we could just do in our calculator or in StatCrunch. So in a calculator, we would either do 2-prop z-test, those of you who might have been clever on this one, or we do 2-samp t-test. Oh yeah, it's 2-samp t-test if we're in the means land. And in StatCrunch, it's even nicer. When we go to stat, we're either doing proportion stats, and then it has a 2-sample option. And same thing with this one, we go to t-stats, and then there's a 2-sample option. So pretty straightforward in terms of actually doing these things. And so that's not something I ever test. So if you want to put on this like not tested, you might have to do it in your project or in a knowledge check, one of all these optional knowledge checks, but I'm not going to ask you to do that. What I'm going to ask you to do potentially is to, make a conclusion given a test statistic and a p-value. And our conclusions still follow the exact same thing we saw before. So our conclusions are still about p-value is less than alpha, reject the null, or p-value greater than alpha, fail to reject the null. Our conclusions are going to finish the exact same. There is enough evidence to say that the proportion of people who improve when swimming with dolphins in terms of depression is higher than those who don't, or there isn't enough evidence to say that the type of bike frame affects the average commute time, right? Or that the average commute time for a carbon fiber bike is different than the average commute time for a steel frame bike. So that's the idea and the takeaway of what you were supposed to get an introduction to with that card sort. And this is the pieces I care about, right? If I give you on the final exam, I want you to be able to make a conclusion based on a test statistic and b-value. I want you to be able to identify what our hypotheses are, and of course, tell me if it's even appropriate for me to use this test based on the conditions. As we move into the project, same pieces. The StatCrunch is going to do all of the actual calculations for you, and the important thing is that you set up the actual hypotheses, you know how to check the conditions, and then you can make a conclusion based on what StatCrunch gives you out.